In this micro lecture I want to introduce you to the idea of Guttman scales. In Guttman scales we try to measure latent traits, including the position or an opinion about a specific topic, the attitude you have, or the level of knowledge you have. And as example I will use the idea of having mathematical abilities. Very simple one, addition. Latent traits are measured by specific items. So we've got a latent trait which ranges between low and high and is general and abstract, like mathematical knowledge about addition, and we measure that using specific items. Now, if you score high on the latent trait, we expect you to answer most questions correctly. If you score low, we expect you to answer most items incorrectly, meaning that the items are associated. Items can be very different. Dichotomous items, for example, or open-ended questions. Now, let's take the example of an open-ended question, 1 + 1, and just ask the candidate or the respondent to answer that question. That's an open-ended question, and the correct answer cannot be guessed. Let's have a look at the relationship between the latent trait and a specific item. Of course, the mathematical knowledge of person A is somewhere along the line, somewhere along that latent trait. And we can now try to predict the chance that that specific individual answers the question correctly. We've got 4 items. The first item is 30 + 3, 30 + 12, 33 + 12, and 33 + 18. Now I've ordered these questions in a specific way. Now, what is the chance, denoted with P, that a person answers one of these questions correctly given the score on the latent trait? Now, of course, these are very simple examples, but you can imagine that if we ask these to very young children, not all of them will answer the questions correctly. Now, the relationship between the latent trait, so how much you know about a specific topic, and the item score can be summarized in an item trace line or an item characteristic curve that looks like this. If you know nothing about a topic, you will answer the question incorrectly, and there is no chance of guessing the correct answer. Once you know a bit, you suddenly know, oh, this is the answer, and you answer it correctly. Of course, the second item, the second question that we posed, was a bit more difficult. So we expect only those that score a bit higher on the mathematical ability scale to answer the question correctly. But we also expect that if you can answer the second question correctly, you can answer the first question correctly, because the first question is more simple, it's less difficult. And the same is true for item 3. So if you can answer question 3 correctly, you will also more or less automatically answer item 2 and item 1 correctly. And for item 4, which is the most difficult one, if you're able to answer that one, you're probably able to answer item 3, 2 and 1 correctly. Now, this idea underlies Guttman scaling. And the difference between the items is called the difficulty, the differences in the difficulty of the various items. And the relationship between the percentage of people answering a question correctly, or the chance that you answer a specific question correctly, which is shown in the graph here, is called the item trace line or the item characteristic curve. In the Guttman model, we expect that items are ordered like this. So in this example, the order is 1, 2, 3, and 4. We expect that 1 is simpler than 2, is simpler than 3, is simpler than 4. And this implies that answering item 4 correctly, you also answer 1, 2, and 3 correctly. Also, the respondents can now be ordered on the latent trait. We're not just ordering the items, but also the respondents. Because if you can only answer 1 correctly, you're more to the left on the scale, but if you're also able to answer 4 correctly, you're more on the right side of the scale. So we not only order the items, but also the respondents. Now, how do we find out what the correct order of the items is? Here is just a set of data. So person 1 to 6, person N at the very bottom, and if you answer the question correctly, you get a 1. If it's incorrect, then you get a 0. Now let's first have a look at whether item 2 or 3 is actually more difficult. Now the simplest way to find that out is just have a look at how many people answer the questions correctly. 6 out of 7 answer item 1 correctly, 4 out of 7 answer 2 correctly, 3 out of 7 only item 3 correctly, etc. So apparently item 2 is less difficult than item 3. So now we can order the item using the percentage of people answering the question correctly. Person 6, however, has a very strange order. You see that this person answers item 1 correctly, but not item 2, but answers then item 3 correctly again. All the others have a more simple relationship between the items and their individual scores. We can now not only order the items, but also the individuals. These are exactly the same data, but we ordered the respondents a bit differently. We ordered them on the basis of the number of questions they answered correctly. So this is how we can order both items and individuals. The problematic person, of course, is person 6, because that person answered 2 questions correctly, but not in the order we expected. So what do we do with this specific individual? Of course, we can now say that the person 3 is on the left side of the scale and person 2 is on the right side of the scale. So we can order them using a latent trait, but that's a bit problematic for person 6. Let's have a look at the relationship between item 1 and item 4. We leave out person 6 in this comparison. Let's have a look at the association between the 2 items. We expect these items to be associated for the simple reason that they are measuring the same latent trait. Here is the combination of the incorrect and correct answers. Now, a simple view on association would focus on the diagonal, so these 3 cases. But since item 1 is much simpler than item 3, quite a few individuals answer item 1 correctly, but item 4 incorrectly. So at first sight, there is not a strong correlation, whereas there is a very strong association between the 2 items. So make sure that you do not mix up the idea of correlation and association. In scale construction, we look in a more general way at the association between items. How do we assess the quality of a Guttman scale, or rather of a Guttman model? Both the items and the respondents are ordered. Which ordering of items and persons gives least errors, like person 6, because person 6 does not fit the model. So we need to take into account the possibility that our model, that items are ordered and individuals are ordered the way we discussed here, is wrong. And of course we want to have a model with least errors. Now, a first indication is the percentage of respondents violating the order described by the model. So the number of persons, like person 6. But some seem to make more errors than others. So this is only a very first indication of the quality of our model. A simpler way is to look at the index of reproducibility. In step 1, we order the items from easy to difficult, and then in step 2, we determine for each mixed type the smallest number of correct-incorrect answers to be changed into incorrect-correct, so it would be reversed, in order to create a simple pattern. This is a rough description of the specific procedure used by Guttman. Others have used a slightly different procedure to determine the number of mistakes, the number of Guttman errors. Now in this case, person 6 can be set to change either item 2 to correct or item 3 to incorrect, so there is 1 error made here. Others would argue that 2 errors are made here, but the simplest way of looking at the scale is here to say that you have to change only 1 of the 2, and say there is 1 error made. Now, how many answers are given? That is the number of respondents times the number of items. So in this case, we've got 7 respondents, 4 answers, so 28 answers are given, and only 1 of them is wrong. So the total number of errors divided by the items times the number of respondents is called the index of reproducibility, and it should be high, otherwise the Guttman model is rejected. We cannot describe the data using the idea of a Guttman model. There are a few difficulties with the Guttman model. It's very deterministic. You have errors. There is not a kind of chance interpretation, and therefore it cannot be tested. You can only argue that the percentage of errors should not be too high, but that idea cannot be simply tested. In this micro lecture, I've introduced you to the idea of a Guttman model, the relationship between a latent trait and the items. We have discussed the idea of item trace lines or item characteristic curves that have a very specific shape in the context of Guttman scaling. I've introduced you to the idea of item difficulty and to Guttman errors and the index of reproducibility.